This is a plant science center, as I'm sure everyone knows. We are dedicated to using plant science for the benefit of humankind. And since the early days, we have concentrated on 3 goals. One is to help to understand how better to feed the world and prevent malnutrition. The second is to help to preserve and enhance the environment. And the third, to help St. Louis to become a world center for plant science.
What I would like to do this morning is introduce you to St. Louis as a center for algal biofuels research. And as you can see on the slide here, in the last year and a half since we've established the Enterprise Rent-A-Car Institute for Renewable Fuels, there have been a number of major awards achieved here focusing on algal biofuels research. The initial investment that Dr. Danforth mentioned from Enterprise Rent-A-Car Institute was really the catalyst for a series of awards that have come in the last 18 months. That initially included a project funded by the Department of Defense through the U.S. Air Force Office of Scientific Research. That's an algal omics project, transcriptomics, genomics, metabolomics, and it includes investigators at UCLA, Scripps Institute. Actually, it's Scripps Institution. I'm always told I should say it correctly. Scripps Institution for Oceanography, Michigan State University, and also the National Renewable Energy Labs in Golden, Colorado. We're also supported by the National Biodiesel Board. Dr. Danforth mentioned the Energy Frontier Research Center. The one that is based here is the Center for Advanced Biofuel Systems. I'll introduce you to that in a little more detail in a moment. The Photosynthetic Antenna Research Center is based at Washington University in St. Louis. I'm a co-investigator on that program, and it really complements and dovetails in very well with the Center for Advanced Biofuel Systems, as I'll show you in a moment. And then you'll hear in detail about the National Alliance for Advanced Biofuels and Bioproducts from Dr. Jose Olivares, who is the executive director, and so he'll follow very shortly. Of course, the drivers for the interest in algal biofuels are the 3 that are indicated here: economics, security, and the environment. And all of these are heading in directions that are not favorable in many senses. Of course, the price of energy is going up. We're seeing a greater dependence on foreign energy sources in the United States. And then there's the concern about global CO2 emissions and its impact on the environment. So really, energy is the hot topic these days. And so we're looking for alternatives to the carbon-based energy sources that we've been using historically since the Industrial Revolution for over the last 100 years. And so one of those renewable energy options, of course, is biofuels. Biofuels have a number of advantages, of course, as an energy system. They're sustainable, they're not extractive technologies that can reduce emissions, provide energy independence potentially, and a more decentralized energy economy, which is likely, as you'll see in a moment, to employ a lot of people in the future. The major constraint really, though, is the low energy density of solar radiation on the surface of the Earth. And so there's little that can be done to change the influx, of course, from solar radiation, but there are major changes that are potential in terms of increasing the efficiency of harvesting that energy and then converting that energy into a usable fuel supply. This figure gives you a handle on the potential number of jobs that have been generated just in the last 20 years in renewable energy sector. And you can see that the biomass in particular employs the most people among all the sustainable or renewable energy systems that are currently underway. And the expectation is, since it's a very labor-intensive process, is that it'll continue to employ many more people than the alternative technologies that you see here. So here, as Dr. Danforth mentioned, we're very interested on algae at the Danforth Center. We also have a number of research programs focusing on oilseed crops, in particular camelina as a model system. This is a close relative to canola, but also to Arabidopsis, so it's a great model genetic system. In this picture of these algal cells that you see here, that large sphere that's inside the larger sphere is actually an oil droplet. And this particular species of algae, under the conditions that it was grown, will accumulate up to 70% of its biomass as neutral lipids, or triacylglycerols. And it's that feature, as well as its very fast growth rate, the ability to harvest 100% or all of the biomass and not leave behind the roots, the stems, and the leaves, that were particularly attractive for algae as an alternative to terrestrial cropping systems. With respect to the domestic security issue, the Department of Defense is particularly interested in the fact that with algae you can harvest oil potentially all year long, every day of the year. And that's attractive to the Department of Defense because then you're not relying on a cropping system that may produce a product only once a year, and if it were to fail, then you would be without a product for a long period of time. In the case of algae, if the systems go into failure, it's very easy to get them back up online, and the lost time is minimal. So this was a very attractive feature. But another important issue with respect to algae that really distinguishes it, of course, from terrestrial crop systems is its ability to capture carbon dioxide. And so we can pump CO2 into ponds and convert that into bicarbonate, which is a non-gas. That bicarbonate is then actively pumped into the algae and reconverted back into CO2, elevating the internal CO2 concentrations and then actually fertilizing photosynthesis to make it more efficient. So this is in contrast to terrestrial systems. Of course, they capture CO2 from the atmosphere. By the time the CO2 is in the atmosphere, it's really already a greenhouse gas. So another important parameter that we in the algae community like to point out is that relative to terrestrial crop systems, algae have anywhere between a 2 to a 10-fold increase in productivity per unit land area. And so this suggests that algae are more efficient at producing biomass, and in fact they are. In part, that's related to their ability to concentrate CO2 inside of the cells. This map gives you a relative idea of the area that would be required to replace the US gasoline supply in 2006. And this larger yellow box would be the area required if we were to depend solely on corn-based ethanol. The smaller box is the actual corn crop. So it's pretty clear that corn is not going to be the solution to the energy problem because we also have to eat, of course. However, the second generation biofuel systems, which are cellulosics and hemicellulosics, would require much less area to meet the US gasoline needs. And that's in large part because you're harvesting more of the material, of course, not just the corn cob, but all the biomass. And then here are the worst and best case scenarios for algae. And you can see under the best case scenario, it's the smallest of the land areas projected. So as Dr. Danforth mentioned, the catalyst for getting this project started here at the Danforth was really the donation of the Taylor family. And the first major project that came in was the Center for Advanced Biofuel Systems. This is a program that really addresses what are the metabolic bottlenecks in the conversion of solar energy into biomass. And so CABS focuses on all of the downstream processes from primary photochemistry and photosynthesis all the way to the production of lipids and novel products. We have two model systems, algae and camelina. They both produce oils.